Agentic AI refers to AI systems that exhibit a high degree of autonomy, decision-making, and the ability to interact with their environment to achieve specific goals. These systems are designed to take actions based on input and feedback to accomplish tasks in a goal-directed manner. Agentic AI typically involves a combination of decision-making algorithms, learning mechanisms, and environment interaction, often used in complex applications like autonomous systems, robotics, and intelligent personal assistants. In the context of large language models, LLMs, Agentic AI can use these models to generate natural language responses, make decisions, and interact with other systems or users. These models can be used to build agents capable of performing specific tasks by dynamically assessing situations and taking appropriate actions. Under the hood, how agent-based AI works. Here's an in-depth explanation of how Agent AI works, broken down into the essential components and processes involved. 1. Definition of an agent. Agent. An agent in AI is a program or system that can autonomously perform tasks in an environment without direct human control. It perceives its environment through sensors, which can be data inputs in the case of software agents, and acts on it through actuators, which could be the system's responses or actions based on the task. Autonomy. An agent operates autonomously, meaning it can perform its task or adjust its behavior based on external factors without human intervention. Rationality. Agents are rational in the sense that they are designed to act in ways that will maximize their chances of achieving the goal or completing the task they were assigned. 2. Key components of agent-based AI. Perception. Sensors. Agents interact with their environment through sensors. In the case of software agents, these sensors could be inputs such as data streams, API responses, or user input. For example, in the case of a chatbot agent, the sensor would be the user's input, text or voice. Actuation, effectors. After perceiving the environment, agents take actions using actuators. In software agents, actuators are typically outputs like database updates, generating responses, or interacting with other systems, e.g. API calls. For example, a digital assistant agent may generate a response based on input or trigger actions like setting reminders or sending emails. An agent typically has a knowledge base that contains the information it has gathered over time. The knowledge base can be static, predefined data, or dynamic, constantly updated based on interactions or feedback. The agent uses its knowledge base to make decisions. For instance, in an AI-powered recommendation system, the knowledge base might include user preferences, past actions, and behavioral data. Reasoning and decision-making. Inference. The core of an agent's decision-making process is its reasoning system. The agent uses logical reasoning, like rule-based systems or machine learning models, to evaluate the available information and decide on the best course of action. Planning. Some agents, especially in more complex systems, may also engage in planning. Planning involves creating a sequence of actions that the agent will perform to achieve its goal, taking into account the current state of the environment and potential future states. Learning. In more advanced agents, learning mechanisms such as reinforcement learning, RL, supervised learning, or unsupervised learning are used. The agent learns from its environment and feedback, adjusting its behavior to improve over time. Goal setting and motivation. Agents usually work toward specific goals. A simple agent may have a single goal, like answering a question, while a more complex agent might have multiple goals, e.g., understanding context, answering with an explanation, etc. These goals can be predefined or dynamically updated based on environmental changes. A goal-setting mechanism determines which actions the agent should take next to fulfill its objectives. 3. Types of agents. These agents are triggered by stimuli from their environment and act based on predefined rules or conditions. For example, a thermostat is a simple reactive agent that reacts to temperature changes and adjusts the heating or cooling system accordingly. Deliberative agents. These agents have a reasoning process to assess situations and decide on actions. They may have models of the world and can simulate different scenarios to choose the best action. These agents are often used in complex domains like robotics and autonomous vehicles. Learning agents. These agents improve their performance over time by learning from their experiences. For example, a recommendation system like Netflix or YouTube learns user preferences through interaction data. Multi-agent systems, MES. In MES, multiple agents work together or independently to achieve a common or individual goal. These systems often involve collaboration, negotiation, or competition between agents. A famous example is AlphaGo, where multiple agents interact with one another to play the game of Go. 4. Interaction with other agents or systems. Coordination. In a multi-agent system, agents coordinate their actions to solve tasks that require collaboration. Coordination might involve communication protocols, exchanging information, or negotiation, deciding on a common plan. Competition and cooperation. Agents may compete for resources or cooperate to achieve shared objectives. For instance, in the case of virtual assistants or customer service bots, multiple agents can communicate with one another to address complex queries that involve diverse topics. Mar 5. How Agent AI uses external APIs or models. Many AI agents rely on external systems, models, or APIs to obtain necessary information or perform certain tasks. For example, an agent that answers user queries may use a generative model API, like Gemini, GPT, or others, to generate responses based on the context provided by the user. Example: in your case, the agent uses the Google.generative AI API to generate responses by passing tasks and prompts. The interaction with the Gemini API allows the agent to leverage advanced AI capabilities for content generation, where the agent sends a prompt to the model, and the model processes the information to provide a relevant response. 6. Why Agent AI is powerful. Task specialization. By creating agents with specialized tasks, such as a taskmaster, data expert, or economist, you can create highly effective domain-specific systems that outperform generalist models. Each agent can be optimized for specific tasks, making them more efficient and accurate in their respective domains. Scalability. Multi-agent systems can scale efficiently. When tasks are complex or need to be split into smaller subtasks, multiple agents can work in parallel, increasing the system's overall throughput and efficiency. Adaptability. Agent AI systems can adapt to changes in the environment and improve over time. With learning mechanisms, an agent can refine its behavior, optimize its actions, and better serve its users or solve problems. 7. Challenges with Agent AI. Complexity. Multi-agent systems can become extremely complex, especially as the number of agents increases. Coordination, communication, and decision-making must be carefully managed to prevent issues like conflicts or inefficiencies. Ethical concerns. Agent AI, particularly when interacting with humans, must be designed to ensure ethical behavior. This includes ensuring transparency in decision-making, avoiding biases, and maintaining privacy and security. Reliability. Agents may encounter situations where they cannot handle unexpected inputs or fail to achieve their goals. Handling failure gracefully and ensuring agents don't take harmful actions are key concerns. Code summary. The create agent function is used to create different agents with different tasks. The use agent function is used to generate a response for each agent based on a shared prompt. The interact with multiple agents function handles multiple agents and gathers their responses in parallel. Consolidate and summarize responses. This new function combines the responses from all agents into a single string and then prompts the model to generate a summary of the combined responses. It joins each agent's response in the combined responses string and creates a new prompt asking for a summary of the entire conversation. Summary generation. After gathering individual responses from each agent, the combined responses are passed to the generate content method of the Gemini model for summarization. Flow of execution. Step 1. The agents are created and each one is tasked with answering the same prompt. Step 2. Responses from each agent are collected. Step 3. The responses are consolidated into a single string and the model is used to generate a summary of the combined answers. Example output. Individual responses. The program will print out the responses from each agent: AI agent, data expert, economist. Consolidated summary. After combining and summarizing the responses, a consolidated output will be displayed. At its core, agent-based AI involves creating autonomous, intelligent systems that can interact with their environment, make decisions, and act in ways that achieve specific goals. Whether a single agent or a network of interacting agents, these systems rely on perception, decision-making, learning, and communication to function. With advancements in generative AI and multi-agent systems, these agents can work together to solve complex problems, offer personalized experiences, and drive efficiencies in various industries. Isn't it exciting? Happy coding!